Good morning, folks. It is Wednesday. What's the date today? March 11, 12, March 13th, I think. No, not March. It's May 13th. Um, Day whatever. You can see up there. I'm keeping track of the number of days I've been down here, teaching from my basement. Hope you're having a good day so far. Mine's pretty good so far. Thank you for asking. Um, Right. So, what are we doing today? Um, so we're getting kind of close to the end of this first sort of major unit in physics this spring. You've been working with and you've been thinking about um, motion, kind of very basic, simple motion in a variety of ways. You've been making graphs like the one you see behind me. Um, And now what we're going to do is we're going to get a little more serious about how we can use these graphs to answer all kinds of questions and predict all kinds of things about objects in motion. Um, so that's what we're going to do. Now, as I'm pouring this coffee, let me just say that in a lot of physics classes, at this point in the game, you would start to get all of these equations. And what typically happens is the people who are in those physics classes start to get a little overwhelmed because it's like, are you serious? Do I really have to memorize all these equations? And that's how it goes. Now, here, what I'm going to show you is, I don't want to say it's a hack, but it's kind of like a hack to where you don't really need to learn any new equations. All you really need to know is how to find the slope of a line, which you know how to do, and you also need to know how to find the areas of triangles and rectangles, which, again, I think you know how to do. If you can do those things, then you don't have to memorize any equations, okay? Sounds too good to be true, but it's not. All right, so, that's good. All right, so I'm gonna erase the board and say a few things while I'm doing that. Let me scoot my desk in front of here. Okay, move that so I don't spill it. Grab my eraser. Okay, so yeah, so we talked about two different kinds of graphs. We've talked about position graphs, and we've talked about velocity graphs, okay? And again, it's important to know the difference, right? So the position graph tells how position changes over time, and velocity graph shows how velocity changes over time. And the name or the word that we use for change in velocity is acceleration, okay? Acceleration can be positive if an object is speeding up. Velocity can be negative, or acceleration can be negative if the object is slowing down, okay? I don't like to use the word deceleration. Acceleration is acceleration. It's either positive or negative. So anyway, um, so what I'm going to do eventually is talk about the answers that were at the end. There was two questions at the end of the velocity versus time graphs of motion homework assignment that I know were probably pretty complicated for you. So I'm going to get to those. But first, let's think of a different example. So you can take some notes about this. Let's just say very basically, I've got a, I don't know, what do we want to do? A dog. Dog is walking at constant velocity of 5 meters per second. Okay? Real quick, I can just throw together the two graphs here. Position time, velocity time. Okay, this is going to be very kind of rudimentary graph, but it'll get the point across. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So position time graph, if it's going 5 meters every second, then we know this is going to be a line with a slope of 5. The slope of the position time graph is the velocity. Let's assume it starts initial position. Who's texting me? Oh, my wife. My dog Cody is ready for his walk. He can wait. Um, so, so 1 second, 5. You get the idea. So there it is. Position time graph, pretty straightforward. No pun intended. All right. Now the velocity time graph looks different because the velocity is constant, right? Velocity is constant. So at 1 second, 1, 2, 3, 4, 5. At 2 seconds, 5. At 3 seconds, 5. For all of the seconds, it's 5. So you've got this horizontal line that represents the fact that the velocity is not changing. Now here's the hack, I suppose you could say, and here's what's really useful about these velocity time graphs is if you want to know how far, what was the displacement, I suppose you could also say, of this dog after 3 seconds. Well, you could probably do that in your head because you're thinking, well, it's going 5 meters per second. Every second it moves 5 meters. 5 times 3 is 15. Right, so how far after 3 seconds? The answer is 15 meters. And you're like, big deal. I thought you were... But, so another way to look at this is, what is the area? If I'm talking about how far after 3 seconds, so from 0 to 1 to 2 to 3 seconds, I'm going to kind of close in that graph. I'm going to draw a vertical line from 3 seconds up to where it intersects with the graph itself. And then I have this rectangular region that I'm going to shade in, and I'm going to ask the question, what's the area of that? What is the area of that rectangle? Well, how do you find the area of a rectangle? A equals base times height. What's the base? What is the magnitude of the base here? Well, it's 3 seconds. And what is the height? Well, the height is 5 meters per second, right? So if you think about it, I'm going to actually do this calculation here. Area equals 5 meters per second times 3 seconds. 5 times 3 is 15, and then check out what happens with the units. What's a meter per second times a second? Well, the seconds cancel, correct? Leaving you with just 15 meters. So this is the big thing. This is super important, and I'm going to be saying this over and over and over again. Area under velocity time graph is distance moved. Put a box around that. Area under velocity time graph is the distance moved. Okay? All right. I can hear my dog barking right now, so I'm going to cut this one off, and then we're going to do another example just like this, except the velocity is not going to be constant. So I'll be right back.